So today's format will be, we will basically have conceptual overview of the topic. I'll also show you some demos on my side. Usually we have full-blown courses available on these particular topics and so on, and that's where we usually also have the lab portion as well, where you are usually able to connect to the lab environment, perform your the hands-on activities, etc., and so on. But for this particular session, we don't have any lab environment for you guys. I do have the lab environment or the virtual machine on my side, but I'll be showing you some of the demos. But in the full-blown course that we usually have, we do have hands-on activities where you're usually assigned a virtual machine where you can perform various activities. Okay, so today's topic is architecting microservices with Kubernetes, Docker, and Jenkins. Jenkins will be utilized for the sake of implementing continuous integration. Then one small request. So I'm under the weather. I have sore throat, so I'll do my best to speak as loud and clear as possible. If you have any issues, let me know. I'll repeat it again. Rather than showing you each and every sort of PowerPoint slide, it's not really PowerPoint slide, it's sort of the PDF slides. So rather than showing you each and every slide, I'll focus on the important concepts, then you can keep the rest of the stuff as sort of reference material. And I'll also try to show you some demos on my side and so on. And like I mentioned, we will also be able to provide you the recorded version of this particular session as well. So because, so we are recording the session, you'll be able to access the recorded version later on. There are about 6 chapters in this particular session. We will have a microservices overview, what exactly a microservice is, why use it, what are the benefits, how it compares to service-oriented architecture, and so on. So that's what we'll cover in this particular topic. After that, we will have overview of REST services. So if you're using, let's say, SOAP-based services, or maybe these days you're also using REST-based services as well, because it's a very popular area now. And REST services, they have been in place for quite a long time now. So if you're using it, well and good. If not, we will have overview of REST services, and we will see how microservices can benefit from this REST services concept. Then module number 3, that's where we will discuss Kubernetes. Kubernetes-wise, we have actually a couple of topics or a couple of chapters. We will discuss some of the core concepts of Kubernetes. Then I'll show you some more advanced concepts. I'll show you some demos on my side, how we can utilize Kubernetes, what exactly Kubernetes is, how it fits into the microservices architecture design, and so on. Then chapter number 5 is about Docker. Actually, what we will do is we'll change the sequence of the chapters a little bit. Before Kubernetes, I'll actually cover Docker, because Docker or Kubernetes will make more sense if we know Docker. So I'll move Docker before chapter. So we will cover Docker before chapter number 3, basically. Then the last chapter is about using OpenShift, Jenkins, and to some extent I'll also cover Blue Ocean. It's basically a plugin for Jenkins, which enhances the user interface or the user experience, which is provided by Jenkins. And we will discuss what exactly OpenShift is, how we can utilize it, what are the benefits of using OpenShift, and so on. So these are the topics that we'll cover in this webinar. We'll also take a break as well later on. So halfway through the session, we will take about 15-minute break. Okay, so let's start off with microservices overview. So what exactly microservices are, why use this concept? Aren't you already using this sort of concept in one way or other? If not, how can you migrate to this microservices concept, and so on? We'll also compare microservices to services-oriented architecture as well. Now, for this purpose, rather than jumping into the official slide that we have here, what I've done is I've prepared a summary of some of these topics. I'll provide you a soft copy of the additional documents as well later on. Okay, so let me show you some additional slides. I'll also provide you a copy of these as well. These are sort of the summary of some of the topics that we'll be covering today. Okay, so let's start off with microservices. Microservices, by definition, are small autonomous services which work well together. Now, what exactly is the meaning of small? How do we know something is small or large and so on? So basically, it's all relative. You have to decide for yourself whether the design that you have created for your system, is it granular, is it small enough, or it's still at a very large scale. There are definitely some principles that we should be aware of in order to decide whether we are following microservices properly or not. So I'll talk about the principles in just a bit, but generally speaking, rather than creating monolithic sort of systems or lots of huge services that are centralized, we try to decentralize the services. How exactly do we do that? I'll talk about that in just a bit. For that, we usually get to utilize Kubernetes, Docker, Jenkins, etc., and so on. But generally speaking, we try to create smaller components, and they are usually autonomous, which basically means that they are self-governed, they are sort of independent of each other. If you modify one, it shouldn't affect the rest of the components at all. So they're sort of independent of each other. And sure, you can still have some integration as well or communication as well. You can say that one service should talk to the other services and so on. So definitely that is still possible. But overall, we try to make sure that all the components, they are overall independent of each other. And we should be able to make a change to the component without affecting the remaining components, which in traditional enterprise architecture is not often possible, because when you make a change to one component, you will basically have to retest the entire system. You usually have to perform the integration tests for the entire system and so on. So I'll talk about how exactly we create a decentralized, smaller, autonomous services in just a bit. And there should be independent processes in microservices architecture. Each component is an independent process. Now, what exactly is the meaning of independent process? To understand this stuff, before I continue with the rest of the points that I have on this particular slide, let me actually discuss a traditional enterprise application architecture. So typically, we used to have a design like this. We used to have, let's say, 3 layers. We used to have the client-side portion or the user interface portion. Let's say we have a web browser here. So on the web browser side, the user will be able to view some website, which will be composed of HTML web pages along with JavaScript sort of files and so on. And you can definitely utilize some framework here on the client side in JavaScript, like you can use Angular, you can use Backbone, you can use pretty much any, like a React, etc. and so on. You can use pretty much whatever framework you want on this client side. So definitely you can do that these days when you're following the microservices architecture, as well as you could have done that when you were following the enterprise application architecture, the classic enterprise application architecture. So if this is your, let's say, the client side, let me change it to this one. Okay, so if this is, let's say, your client side, the client browser basically, then in between we will have the network involved. Then on this side, you will have some application server or some web server and so on. So on this side, on the server side, you can have pretty much any type of server-side technology. Like you can have Java, you can have .NET, like you can have ASP.NET Web Form, or you can even have ASP.NET MVC, etc. You can have PHP, Ruby, whatever server-side technology you want to use, you can do that here. And then we usually have database as well on the server side. So database-wise, you can choose to utilize some relational database management system like Oracle, SQL Server, DB2, etc. Or you can choose to use NoSQL solution as well. Like these days, we have quite a few options, like we have MongoDB, etc. and so on. They are NoSQL sort of databases where basically we get to store the JSON sort of data rather than storing the data in traditional way, the relational database management sort of way. We get to store data in sort of object form and so on. So it doesn't matter what database we have on the server side, whatever server-side technology you have, it can connect to the database. And then on the client side, we have HTML pages along with JavaScript, etc. and so on. They can make requests to the server side, which in turn can open connection to the database. retrieve data, and then return data back to the client and so on. So traditionally, we used to have architecture like this. Now, there are lots of drawbacks of this particular architecture. Before we discuss microservices, let's discuss some of the drawbacks of the traditional architecture. Okay, so drawback number one is that it is not a very scalable system or design. Scalable means that what if you need to have database stored or installed on one machine in one part of the world, and you want to have this web server on installed on a totally different web server in totally different area of the world, and then you want client to communicate to that web server. If you want client to connect to your web server, there's a chance that client will have to access your web server, which is located several thousand miles away, which can slow down the performance basically. So performance will be one drawback. There's next to no scalability here at all. Another drawback is that your database is not known to the application developer. So whoever is writing the code on the server side will have direct access to the database. So having direct access to the database can be a good thing as well as a bad. In most cases, it will be a bad thing, especially when you have, let's say, contractors involved. So if you ask someone to develop an application for you and you're just hiring that person temporarily, then you'll basically end up providing connection in, details to the person. So you're basically connected to the database directly. So that's usually a bad thing. So maybe you want to secure your database so that no one should be aware of the actual database location. Secondly, maybe you want your system to be more flexible in a sense that down the road you want to be able to change your backend, your let's say data storage. Rather than using, let's say, Oracle, maybe you want to switch over to SQL Server or to some other database solution. Then in that case, if you make a switch, you will have to change the code that you have written here. So changing the code in your actual application will be way too much work. So rework should be avoided basically as much as extent as possible. You should avoid the rework basically. So there are quite a few drawbacks of this particular architecture. Sure, you can say that we are already familiar with services. We can create web services. So if you're already familiar with how to create web services, well and good. If you already have it at work, well and good. If not, let me give you a quick overview of that as well. So to make this system more scalable, what you can do is you can still have your database here, and here you can have your, let's say, the service layer. Before service layer, one more small thing which I forgot to mention here was that definitely you can say this is your, let's say, the server-side portion, and here you can still have reusable components, like you can have data access layer, you can have business logic layer. So definitely you can have these reusable components, like in case of Java, you can have these as jar files. In case of .NET, you can have these as DLL files. So data access layer will be responsible for connecting to the database. Business logic will be responsible for adding some business validation rules, data validation rules, and so on. And then your application or the server-side code can connect to the business logic layer, which in turn can talk to the data access layer, which in turn will connect to the database. But still, this is not very scalable. So to make things more scalable, you can still have your data access layer, business logic layer, etc., and so on. And on top of that, you will basically end up creating a service layer. Service layer is basically being able to expose the functionality of, let's say, the business logic layer or even the data access layer, or in short, exposing the database tables over the network as functions, as services in short, basically. So you can now create services like SOAP-based services. Like traditionally we used to have SOAP-based services, but these days we prefer using REST-based services in most of the scenarios. So you can create a service layer here, which will expose your database over the network now. And then any application developer can use, let's say, Java or .NET, etc., or PHP, and talk to the service layer basically. So you still have Java-based code or .NET sort of code here, but now it's talking to your services. And the benefit of this approach is that now these developers, they are not directly connecting to the database. They don't even know what's the actual location of the database. That's one benefit. And second benefit is that down the road, if you have to change your, let's say, a database solution, you want to switch over from one technology to another, like Oracle to SQL Server or vice versa, then you'll just have to update your service layer portion. You'll not have to update your actual portion, which is sort of directly connected to the web application and so on. And then you'll still have your client browser, which will end up loading HTML, JavaScript, which will end up talking to this server-side code, which in turn will talk to the service layer and so on. So basically, you're exposing your database over the network by creating services. For that, in the past, we mostly used to rely on SOAP. Sure, even these days you can use SOAP as well, but in most scenarios, you will want to prefer using REST services, which I'll talk about in the next chapter. Okay, so basically you have utilized something that is known as service-oriented architecture to expose your database as a service over the network. And you're able to now connect to it in various ways now. Like you can connect to it by using this web application, or you can also choose to create a mobile application like an iPhone, Android sort of application. Even that can talk to the service layer and sort of perform CRUD operations, create, retrieve, update, delete sort of operations at the database level and so on. You can choose to create a desktop-based application, console application. So sky's the limit. You can choose to create any type of application now. Whereas without the service layer, you were very, very restricted. You had to create just a web application. You had to talk to the database base directly and so on. Whereas now you're able to create pretty much any type of application. And you can actually create another service. So rather than creating a web application, you can say you want to create yet another service which should talk to this particular service layer. So you could say we own this particular service and we want to let some sister company or some other organizations have access to our service layer as well. So they can create their own service, which in turn can talk to your service, which in turn will talk to the database. And then they can choose to create their own user interface and so on. Like you must have utilized or seen various Google-based services or even services for accessing weather information or currency exchange sort of information, stuff like that and so on. So basically we get to utilize someone else's service and we can choose to expose their service by creating a wrapper around that service ourselves, and we can add more enhancements to it and so on. So basically this is services-oriented architecture. It's nothing new. It has been in place for a very long while. You must have heard of SOAP, etc., and so on. It has been in place for very long. The question is, how does it relate to microservices? Because that is the main scope of this particular webinar. So that is exactly what I'm going to answer in just a bit. So our goal will be to understand microservices. For now, we have discussed service-oriented architecture. To understand microservices, let me show you a simple example here. Then I'll discuss how microservices can be utilized to further enhance that architecture. So in traditional architecture, you will most likely have a single database server. Like if you have Oracle, you will have Oracle only. You will have just maybe SQL Server and so on. And then you'll definitely want to create your application. So you'll end up creating, let's say, your user interface. So user interface will be there, which will be basically a bunch of HTML files, JavaScript sort of files, and so on. And you'll create your either .jsp files or ASPX files, stuff like that, .php files, and so on. We'll have quite a few of them. And you'll want to create these files based on the number of components you want to create. For example, you need to have maybe the product functionality in your application. You'll create the corresponding pages that lets you perform insert, update, delete to the product table and so on. We'll have, let's say, product component. You'll have, let's say, order component. You'll have customer component and so on. But when you have to deploy these things, you'll most likely end up deploying all these to a single web server or to a single application server. If that is exactly what you're doing, if you're deploying all these to a single server, then you're basically following the traditional enterprise application architecture, not the microservices architecture. This is a very monolithic sort of style or design, where we have lots of components, but they're all centralized. All the data is centralized in a single database or a single database server, and all these components are also centralized as a single application in some application server or web server and so on. Sure, on top of that, you can choose to utilize some load balancer for the sake of improving performance and so on, and then you can have some client browser as well, which can then talk to the web pages, which in turn can make use of these server-side components to talk to the database and so on. This is currently very monolithic sort of design. You have overall just a single database server, and overall you have a single application server or web server which hosts pretty much everything. Now, if you're saying that, no, we don't have centralized system like this, we already have a scattered sort of system. We have one database per application, one database per component, one server, one application server, one web server per component, then you're already using microservices. So you're already using microservices if you're not already centralizing everything. If you are centralizing everything, you're not using microservices. In a microservices architecture, you will still have this overall the same functionality. End user will also experience the exact same thing, but at the architecture level, at the design level, they will have slightly different design. So this is actually a very simple example. It clearly explains what exactly a microservice is. So microservice-wise, you will basically want to have a separate database per component. One database per component. So for example, we have order component. It will have its own database. It will have its own bunch of .jsp, .java, ASPX.cs sort of files and so on. So it will have nothing but just order-based functionality, basically. Likewise, for each and every component, you have a database, plus you have its own separate files, etc., and so on. And these are autonomous. These are independent of each other. You can still have some common functionality, or you can say that they can still talk to each other. So these are services. You can still you'll still have the services the way we usually implement the services. Like you can have SOAP-based services, but mostly these days we prefer using REST-based services. So you will have services, the core for the services, and you will have the database as well. And these will be independent components. These will be autonomous. They will be overall independent of each other. And notice that they are smaller components now. Rather than centralizing everything, we are decentralizing things. And later on, we will discuss how we can utilize Docker containers as well as Kubernetes in order to enhance the functionality of these components by adding some fault tolerance, load balancing, and how we can further improve the performance, etc., and so on. So overall, if you split your centralized system into a decentralized system where you have multiple components, each component will have its own database, etc., and so on. That's overall basically a microservices architecture. So coming back to some of these points here, so they are independent processes. So each component, like orders, customer, sales, etc., and so on, you can choose to turn off one component without affecting the rest of the components. In most cases, the rest of the components will not get affected, especially when they are not communicating with each other. So you can say that for now, we don't need the sales component. We just need to show the inventory to the clients, and that is it. You can easily choose to take away the database as well as the service portion because it's in a separate container. Containers, Docker containers, that's exactly what we'll discuss in detail later on. For now, if you're already familiar with Docker container, well and good, keep in mind that each component will run it in its own container basis. So you can turn off one component without affecting the rest of the components and so on. So they are independent processes, basically. And they communicate over APIs. So rather than talking to the database directly, they will want to utilize some service sort of API. Like although you can choose to use SOAP services, but mostly we prefer using REST-based APIs, which is something I'll talk about in more detail in the next chapter. So basically expose the functionality of some component or some database over the network by creating a service for it, the APIs basically. They are autonomous, they are self-governed, they are independent of each other. They're small, we are focused on small. We have discussed what exactly small means. So small basically means exactly one functionality. So you need to know what system you are developing, what system you already have. And if you have centralized everything, then you need to identify what are the smaller components. Can you split the system into smaller components? Can you create a separate database for each and every component? Can you isolate the components basically? And for that, we will discuss Docker container as well as Kubernetes later on. Then we have already discussed that microservices is actually a form of service-oriented architecture. So if you recall, I mentioned that in a traditional enterprise application architecture, which usually talks to the database directly, you can choose to enhance it further by adding the service layer, which will let you expose the functionality of some database over the network as a service. So that is service-oriented architecture. But if you take it to the next level, which would be you take your centralized services-oriented architecture and you split it into smaller individual components, so that each component should have its own database, it should have its own sort of a web server, it should have its own application server or some web server, and it should be isolated from other components. And basically that is a microservices architecture. So microservices is not a radically new concept. It is just taking the existing services-oriented architecture and just taking it to the next level, just making it more granular, basically. And when you make things more granular, another benefit would be that unlike the monolithic sort of design, where if you are, let's say, using SQL Server on this side and you are using, let's say, Java on this side, then you will basically end up implementing the entire application by using the same tools, by using the same technology, which is not necessarily a good thing. Whereas if you use microservices architecture, where you have multiple smaller individual autonomous independent components, you can choose to utilize, let's say, Java for this one, .NET for this one, PHP for this one, Node.js for this one. So you can choose to utilize different technology for each and every component. So this way, multiple teams can be involved with different expertise, and they can produce the same result. Overall, you just need to make sure that your overall system works. That is it. Rather than saying we need to hire all Java developers, now you can say that no, we don't care. Or we just need to implement these business level components. That is it. So we can choose to use Node.js, .NET, Java, PHP, whatever technology you want for each and every component. Basically, that's another benefit of using microservices architecture. It's all about making things as granular as possible, but don't over granularize things. Don't make them way too smaller. Just make them small enough so that they represent your business commodities, business domain sort of representation should be there, and so on. And microservices, definitely it will be a very, very handy concept, especially if you're trying to utilize agile software development methodologies like Scrum or extreme programming and so on, because you can create the individual components. You can create the database, you can create the corresponding services, etc., and so on, and you can easily integrate things as well. So integration is actually much easier in case of microservices architecture. Testing can become a bit complex in microservices architecture, but integration becomes much easier compared to your traditional system. Then some of the differences between microservices and classic service-oriented architecture. SOA most often utilizes XML as a data interchange format, whereas microservices uses JSON. It's complex to integrate, whereas microservices, they are easier to integrate. Then SOA is usually, or SOA is usually heavyweight. Microservices are lightweight. They are lightweight mostly because of Docker container concept. So I'll talk about Docker container later on, but you'll notice that they are very, very fast to create. In a matter of seconds, you're usually up and running. You can start a Docker container in very fast manner. Then SOA mostly utilizes SOAP over HTTP, whereas microservices mostly utilizes REST over HTTP. I'll talk more on this particular topic in the next chapter as well when we discuss REST services. Okay, some of the principles that we should be aware of when we are trying to identify whether we are following microservices architecture design or implementing this design properly or not. So number one, we should model around the business domain, which basically means that, like I mentioned, business doesn't care for do you have business logic layer, do you have data access layer, are you using SQL Server, are you using Oracle, are you using Java? Sure, all that matters. Definitely technical things, they matter. We still have to utilize design by creating the data access layer, business logic layer, etc., and so on. But at a higher level, we should mostly focus on the business domain sort of concepts, like business will care for orders system, it will care for customer system, it will care for product system, and so on. So at the higher level, we care for these, and there should be independent components basically, and we should be able to integrate them with these. Then culture of automation. So another important thing in microservices is that since we are focusing on the granular design, we will end up creating lots of smaller components. They will have their own database, their own service layer sort of code, etc., and so on. And we will also end up utilizing technologies like Docker container and so on. So we definitely need automation. We need some tool. We need some software that should let us automate the continuous integration and continuous delivery sort of portion. So for automation purpose, later on we will see Jenkins. So Jenkins is the software that we mostly utilize these days for the sake of having automation in place, for the sake of having continuous integration as well as continuous delivery. So I'll talk about this portion in more detail later on. And we should hide implementation details. Microservices allows us to hide the implementation details. Like if you recall, I mentioned that in the traditional design, you'll most likely end up using a single technology, like you will end up using Java technology for implementing the entire system, or .NET for the entire system. You'll end up using SQL Server or Oracle for the entire system, and so on. So unlike that, in a microservices architecture, we usually have multiple smaller components that are mostly autonomous. They are independent of each other. So basically, due to this, we can say that we are able to hide the implementation details because each component can potentially utilize a different technology, different language, different database, and so on. And decentralize all things. We have discussed this already, that if we have everything centralized on a single server, then it's basically a monolithic sort of design. Whereas when you decentralize things, so rather than saying we should have a single Tomcat application server, a single WebLogic server, we can now have one application server per component, one web server per component, and we should be able to easily turn off any component whenever we want. So we should basically decentralize these things. And we should be able to deploy these components independently. So if there are multiple components, we should be able to deploy the components independently of each other. Definitely, there will be scenarios where you will have some dependency, like one component depends on another component, but overall, majority of the components will be independent of each other. Another principle of microservices application architecture design is that we should isolate failure. So isolation or isolating the failures will be tricky in case of centralized system. If we have one monolithic sort of system where we can say that this thing, this middle piece is a single system, it's a single application. If something has failed, it will be much more difficult to troubleshoot the issues. Definitely you will have log files and stuff like that and so on, but which component has failed, you will definitely have to spend a bit of more time to identify where exactly the system is failing and so on. Whereas In case of microservices architecture, it's easier to isolate the failures because these are individual components. So for example, in case of enterprise architecture, what if your database is corrupted? Maybe some of the records are corrupted. You will have to find out exactly what records are corrupted, what tables they belong to, and so on. Whereas in this case, if some of the records are corrupted, they will most likely belong to a single database. And just that component will not work properly. The rest of the components will still work. So it will be much easier to identify what a component is causing the failure, basically, in case of microservices architecture. So basically, these are some of the principles that are followed when we have to identify whether whatever design we have is using the traditional SOA design or the practices, or it's using the microservices design and the practices. So overall, microservices is not a new concept. It's same as SOA. It's just that we try to make things more granular. Another important thing in a microservices architecture is that we design for failure. The architecture is designed for failure, which means we expect that things can go wrong. We prepare for that as well, actually. And what we do is we get to utilize various tools, like on top of Docker, we get to utilize Kubernetes, which I'll talk about in more detail later on. But the main benefit of using Kubernetes is that it allows us to cluster our component. We can have our component installed on various nodes, which can be part of a cluster, basically. Think of it as automatic failover, basically. So if something has gone wrong, it will automatically fail over to a different component or different node, basically. So in case of Kubernetes, we get to utilize something that is known as a pod. I'll talk about pods in more detail later on. But when you have some pod which has failed, some container, Docker container which has gone down, it's no longer responding, Kubernetes automatically creates a new one for us. And actually, it depending on how it's configured, it creates multiple replicas, so that whenever some container fails, it will automatically switch over to a different container or to a different pod and so on. So I'll talk about Kubernetes, how we usually implement it. I'll actually show you a demo as well later on. So microservices architecture is designed for failure. Failures, they are a fact. They can happen. So we have to be prepared for it, basically. And actually, in real world, we encourage failing the system purposefully, just so that we can test whether Kubernetes, the clusters, they are working properly or not. For that, you can choose to use various tools. For example, one of the popular tools these days is Netflix's Chaos Monkey. So it basically purposefully fails some component, so we can verify whether it failed over to a different component or different node or not, and so on. Some of the benefits of microservices architecture. So microservices architecture heavily promotes having multiple teams, and each team can have different expertise. So rather than saying that we need to have a centralized architecture where we need to have everyone who is familiar with Java, that is it, you don't have to do it that way if you're using microservices architecture. Since each component will have its own database, it will have its own bunch of pages, etc. Definitely, you will have user interface layer, you will have your business logic layer, data access layer in each and every component. But each component can utilize a different technology, different database, different language, and so on, different application server, different web server, and so on. So they can be managed by different teams, basically. We can utilize different databases and so on. Centralized management is minimal, since we try to scatter things. We try to have multiple isolated components, not just on one machine, but potentially on multiple machines, so that even if some hardware has failed, then it should still allow the end users to access the application and so on. And microservices architecture works well with continuous delivery and continuous integration. For that, we often use Jenkins. So basically, you want to continuously contribute towards your final product, which should be composed of multiple components. So maybe you're promoting, you're deploying one component at a time. You're making changes to just one component at a time. So continuous delivery is possible by using Jenkins and so on. I'll talk about Jenkins in detail later on. Then microservices architecture, there are some of the drawbacks as well. So drawbacks wise, since it will be a distributed system, it's no longer centralized. We are not mostly relying on just a single application server or a single web server or single database server. Now we will have multiple application servers, multiple web servers, multiple database servers. So it's more distributed. So definitely we have to now ensure that all these components, they are still able to talk to each other if they need communication. Mostly they will be independent of each other, they will be isolated, but still if they require communication, then we have to keep that in mind that since they are distributed, so we have to expose the port numbers, stuff like that, in each and every container separate. We have to ensure that the database server, the web server, the application server works properly inside the container and so on. And we also have to ensure that they have inter-service communication at times whenever required, and for that purpose we have to open the ports basically. One drawback of microservices architecture, especially when we get to use REST API and stuff like that, is that distributed transactions are usually not possible. So distributed transactions, if you need to have, let's say, order, product, customer, if there are multiple components, they are all using separate databases, different technologies and so on, there's a chance that you'll not be able to implement distributed transactions, mostly because you will end up utilizing REST API and so on. So there are some cons as well of microservices architecture. Overall, it's definitely a very popular architecture. Definitely in quite a few cases, we can choose to implement this particular architecture. In fact, Netflix is using microservices architecture. Flickr is using it. Facebook is using it. Google is using it. Google, in fact, they also utilize Docker as well, Docker containers. And on weekly basis, they create more than 1 billion containers on weekly basis. So definitely overall, this architecture is very popular. Okay, so basically here we have discussed microservices concept so far. Okay, there's a question. Can we say we are moving from the traditional services to fine-grained services? So yes, that's pretty much what we are doing. So previously we used to have very monolithic sort of design. We used to have everything sort of centralized and so on. Whereas these days we prefer having everything decentralized, having everything sort of at a very granular level, so that we can manage them independently, we can reuse them as well, and so on. So definitely, rather than having monolithic design, have granular design. So how granular the design should be, you have to decide that for yourself. You need to identify at the business level what components are required, what components will need communication. Can we potentially utilize a totally different technology for each and every component? If yes, definitely go for microservices architecture. Okay, so so far we have discussed microservices architecture. Okay, there's another question regarding distributed transactions. So distributed transactions, if you have, let's say, the centralized architecture, where did my mouse go? Okay, so the question is regarding distributed transactions. So if you have, let's say, the traditional design, where we are saying that this middle piece is designed by using a single technology, maybe just Java or just .NET or something like that, and we have mostly let's say that we have a single database server. So if we have multiple components, we have product, order, customer, etc., and so on, and they need to have transaction involvement. For example, customer needs to update, insert, delete records, and we don't want to finalize them unless and until order has also modified some of the records and so on. So if order is successful, then we want to update whatever we have in the customer. So we want to ensure everything is updated or nothing is updated. So the whole thing should be updated or nothing should be updated. In case of a centralized system, this is easy because you're using a single technology, you're using a single database server. So this is possible. This is easy in case of the centralized architecture. Having transaction in place is easy basically because it's overall running on a single system. Whereas in case of microservices, keep in mind that they will be isolated components. In real world scenario, they will basically run inside a different Docker container. And potentially they can also be located on a totally different machine. So one machine can have a Docker container which runs or hosts the order component. Second machine or second Docker container will have, let's say, the customer and so on and so forth. So now if you want to have the same transaction sort of concept, then distributed transaction will not be possible, or it will not be easy in this particular case, especially if you are using a totally different technology. Especially when you use, let's say, a REST API. REST API doesn't facilitate in distributed transactions. When you use web services, the SOAP-based services, they do have WS-based add-ons or the plugins or the enhancements, which allows us to implement transactions and so on. But when we use REST API in this microservices sort of architecture, due to the distributed nature of the applications or the components, which are usually isolated as well, distributed transaction will be very, very difficult or not possible in most cases, especially if you are using technology which doesn't even support distributed transaction concept, like when you are using, let's say, REST API and so on, they don't support transactions basically.
Assuming there is a requirement to implement this distributed transaction in industry, what is the best practice and how are they achieving it if they have to do it using REST?
Okay, so if you still have the requirement to have distributed transaction in place, then you can, for that purpose, still utilize the traditional architecture. Plus, you can also rely on some additional techniques, like you can use message cleaning, etc. You can use some database where you can store the data manually for the sake of recording the transaction. So basically, you have to do things manually, or you have to rely on the traditional architecture. You have to rely on SOAP-based service because it does support the enhancements or the plugins or the add-ons which supports transactions. Whereas if you are using REST API, then it's usually not possible. Okay, so this is basically an overview of microservices. Then next, let's discuss chapter number 2. It's about REST API. Okay, or REST services basically. So microservices doesn't really force us to use any specific technology. We can choose to utilize whatever technology we want as long as we are following the design principles which I talked about previously. Like we should isolate the failure, we should focus on the business domain, etc., rather than focusing on having a central monolithic sort of design. We should decentralize it, scatter it, have individual containers where we should have the components deployed, etc., and so on. So overall, it doesn't really force us to use any specific technology, but sure, there are some better practices as well. But there are some tools or technologies which facilitates in implementing this microservices architecture concept. And REST services, they are very, very useful when it comes to designing the microservices. Traditionally, we used to have SOAP-based services. SOAP mostly used to rely on XML-based data interchange format. And one of the drawbacks of XML-based data interchange format is that it's usually fairly huge. The footprint is fairly huge because you have to open the tag, you have to close the tag. You also have to utilize some predefined tags as well, like envelope, body, message sort of tags have to be utilized. So overall, the footprint is fairly huge in case of XML-based services. Whereas if you utilize REST-based services, rather than using XML as a data interchange format, we mostly get to rely on the JSON. You can call it JSON or JSON, it's up to you. It stands for JavaScript Object Notation. It has much smaller footprint because we don't have to open a tag or close a tag at all. We basically just have to use the curly braces, that is it. We do have to specify the name of the property as well, but we don't have to start a tag and end the tag, unlike the XML-based technique. So JSON has much smaller footprint. Another benefit is that these days on the client side, we heavily get to rely on JavaScript. Like on the client side, if you are creating a web application, you will most likely want to utilize JavaScript in raw format as it is, or you'll want to use jQuery, or these days we actually prefer using some sort of framework like Angular, React, Backbone, and so on. So all these frameworks, they are JavaScript-based frameworks. And when you use this JSON as the data interchange format, it is already JavaScript-based syntax. So all the frameworks, even the regular off-the-shelf JavaScript as well as jQuery library, they can easily read this JSON data. So manipulating this JSON is much easier on the client side. So that is another reason why we prefer using REST-based service. And REST basically stands for Representational State Transfer. So representational state transfer basically means the URL determines the state of your service. So what exactly you're trying to access will be determined by the URL. Unlike XML, where the URL just tells us what's the location, what's the address of the service, that is it. Then after that, we have to send data in XML format to the service to tell the service what exactly we are wanting to do and so on. Whereas in case of REST-based services, the URL represents what exactly we are trying to do. And we get to utilize the standard HTTP protocol along with the standard HTTP-based verbs or actions, like we have get, post, put, delete, and so on. So we get to use the web standards basically, something that that has been there since forever, and it will remain for a very, very, very long time to come. Whereas in case of SOAP-based services, things change radically. New add-ons are introduced and so on. We have to then learn the new XML-based tags that have been introduced and so on. Whereas in case of REST-based services, it's mostly the standard HTTP-based protocol. It's this URL basically, the way we usually get to use the URL. Like you can specify the domain name, you can specify the port number, you can specify sort of a virtual directory. It's not really a virtual directory that we get to use in REST, but sort of a virtual directory. Then you can use question mark, you can pass it the parameters and so on. And we get to use the standard get, post, put, delete sort of verbs and so on. So there are various ways in which we can implement the services, XML or SOAP-based services or HTTP or REST-based services basically. But these days, we prefer using REST a lot. All the major organizations like Google, Facebook, etc., they're heavily making use of REST-based services. Okay, so in REST-based services, we get to utilize these verbs or actions. These are all standard verbs and actions. Like we get to use get, we get to use delete, put, post, and so on. Let me give you a quick overview of these here. Okay, so basically get. You might have seen this sort of syntax actually. So get, here we get to specify what page we want to access. And then after that, it usually returns a status code like 400 if there is a client-side issue, or 404 when page is not found, 403 when something is restricted, we cannot access it, or 200 when everything is fine, 500 when server-side error is encountered, and so on. So basically, even when a web browser has to connect to a web server to receive the web page, under the hood, it is using standard verbs or actions like these, like get and so on. So we get to utilize the exact same actions or the verbs when we have to create our own web service as well by using REST-based technique. So we get to use get verb or the action or the method when we have to retrieve data in read-only format. So when on the client side, on the JavaScript or the HTML side, you want to click some button, and then you want to connect to the web service or the application server or the web server, and it should return you data in read-only format. You're not going to make any changes on the server side. So get is used in that case. Delete is also fairly straightforward. Delete is used whenever you have to make some change or when you have to delete a record on the server side. Like especially in the database, you will end up deleting some record. So basically, you get to use these even in JavaScript. Like even if you're using, let's say, jQuery, you get to use $.ajax. Then you get to specify what method you're using. So method is let's say put or let's say delete. So you get to use something like this on the client side in jQuery, or even if you're using some framework or some technology like, let's say, Angular and so on. Like in case of Angular version 1, you get to do something like this, HTTP dot, then you specify what operation you want to perform and so on. And likewise, even on the server side as well, you get to utilize these things basically. Like for example, if you use ASP.NET MVC on the server side, you get to utilize delete annotation before your function name. It tells the web server or ASP.NET that this function should be called when the client is requesting a delete operation. So delete is used whenever we have to delete a record on the server side. Then post is used whenever we want to insert a record on the server side. Put is used when you want to update a few records, few columns on the server side. And we usually have another one which is called patch, or sorry, I forgot to mention this thing. So update means you want to update pretty much everything, or most, let's say. You want to update most columns or pretty much all the columns on the server side. Whereas patch means you want to update a few columns, or you're only allowed to update a few columns, you're not allowed to update the columns. So in that case, you basically get to utilize patch as the verb or action or method. Still, no one is stopping us from saying on the client side as well as on the server side, we want to use get, but under the hood on the server side, we want to perform the delete operation. You can still potentially execute delete operation on the server side if you want, but obviously it doesn't make sense. You'll not want to do it that way. So to standardize things, we usually match whatever action we have used on the client side and the action that we have used on the server side, and then we try to obey some of these rules and so on. Then we try to return some status code. When the service was it returned the data properly, it executed the operation properly, performed the operation properly. It should return 200 as a status code, 400 or 404 when the service is not found, 403 when we had a security sort of issue, when the service was prohibited, we had authentication, authorization sort of issue, and so on. 500 when something went wrong on the server side, and so on. So basically, it's just a brief overview of some of the actions that we have available as part of REST API. The question is, how do we implement REST API? How do we implement REST-based services? So for that, we need to use some technology. So technology-wise, it's up to you. You can use pretty much any technology. Like in case of Java, you can choose to use Spring Boot if you can choose to utilize, let's say, ASP.NET MVC along with, let's say, Web API. So in ASP.NET, we have something that is known as Web API, which allows us to create the REST-based services. Or if you want to utilize JavaScript as a language, you can choose to use Node.js, which allows us to create web services written in JavaScript. So these are some of the possibilities, some of the possible tools or techniques which you can choose to use for the sake of creating a REST-based service. So have a pick. If you're a fan of using Java, you can choose to go for Spring Boot. If you're a fan of using C#, you can choose to go for Web API. If you're a fan of using JavaScript, you can choose to go for Node.js. So basically, you'll want to create multiple smaller or granular services. Pretty much one operation per, or one service per operation. So for example, you can have a service named, let's say, you can, let's say, use get as the action. Then let's say your service name is something like this. So let's say http:// whatever the domain name is, we don't care for it. Then here we can have, let's say, a product sort of scenario. So we can choose to create a service. We can choose to name it products. Then when you use get action, it will connect to this simple URL. It will return you the data. And you can also choose to parameterize the REST API or the REST-based services as well. You can choose to pass it the parameters. For passing parameters, let's say we want to get product by ID. So let's say we have get action. Then again, we have domain. Then you can choose to, let's say we want to get products by ID. So for that, we can pass the ID like this, / whatever the ID you want to pass to it. So this is what we mostly prefer, or this is sort of syntax or the URL which we prefer using when we have to send the parameter to a service. Or you can still choose to utilize the classic technique, which is sort of the query string. You can say we want to pass the value like this. Likewise, when you have to perform more operations, you can choose to use, let's say, delete action. You can say you want to delete some record. So products, you want to delete a product by its ID. So whatever product has the ID 1, you want to delete it. So definitely you have to write the code as well. So code-wise, you can choose to use Node.js, ASP.NET, or Web API, or you can choose to go for Spring Boot as well. Later on, I'll show you a brief example of Node.js-based REST service. But generally speaking, we get to utilize these web standards like these. Unlike SOAP-based services, where we get to utilize lots and lots of XML tags and so on. And microservices-wise, you'll definitely want to create as many services as possible. One service per operation, basically. Now, in case if you have a complex service which needs to perform multiple operations, insert, update, delete, etc., and so on, then for that purpose, still, if possible, try to split it into smaller services. Otherwise, if it's not possible, you can choose to use post for it. So post quite often is used when service will end up performing lots of operations. So here we have discussed some of the concepts basically. So here we have discussed overall URL sort of convention and so on that we get to follow. Later on, I'll show you an example of Node.js based service. But overall, these days we prefer using REST-based services because they help us in creating or implementing this microservices architecture a lot. Okay, so any question regarding this concept? If not, then let's take a, let's say, a 10-minute break. Then after the break, we will discuss Docker. And we have a couple of chapters on Kubernetes. And then after that, we'll discuss Jenkins as well. So let's take a 10-minute break. Okay, let's resume the session. So before the break, we discussed what exactly a microservices architecture is. We discussed that you'll basically want to create multiple granular services, and ideally they should be independent of each other. They can still communicate with each other depending on the requirement, but overall they should be independent of each other. And each component should have its own database. It should have its own services and the rest of the files that need to be there for that particular component and so on. The question is, how do we implement microservices properly or in detail? For that, we discussed REST API to some extent. Definitely, you need to have REST API. And then after that, you'll want to ensure that they are isolated. We should design them for failure and so on. So how do we implement these design principles? How do we isolate them? How do we design them for failure? That's where we have to discuss Docker, Kubernetes, and for automation, we will discuss Jenkins. So basically, so far, what we have discussed is you can create your, let's say, service or services. So say we have one database for now. Doesn't matter whether it's a SQL Server or Oracle, or it can be some NoSQL based solution like MongoDB, etc., and so on. And let's say you have a product component. You have designed the REST API for it, where you have the ability to perform the insert, update, delete sort of operations and so on. So you have basically implemented the CRUD pattern for this product component of your application. So you have created the REST services, and you have also created the database as well. Likewise, you can have other components as well, like inventory, sales, customer, etc., and so on. Now, how do you isolate them? For isolation purpose, what we get to do these days is we utilize something that is known as a Docker container. So what exactly is Docker? So Docker. So basically, I'm changing the sequence of the chapters a little bit. Before we cover Kubernetes, we should cover Docker, so that Kubernetes makes more sense. So Docker is basically a containerization solution. Now, what exactly is containerization? Before that, let's quickly discuss virtual machines or virtualization, basically. So you must have seen various virtualization solutions like VirtualBox, VMware, Hyper-V, etc., and so on. Virtual machine is basically the hardware level emulation or the simulation. So virtual machines are hardware level emulations, which basically means that your RAM and CPU is shared by your virtual machines. So say if you have overall 8 GB RAM at the system level, and you want to create, let's say, up to 4 virtual machines, then you can potentially assign up to, or roughly up to 2 GB of RAM per virtual machine and so on. So you're physically or sharing the resources physically, basically. Physical resources are getting shared. Then inside the virtual machine, you can install any OS you want. Like you can have Linux, you can have any flavor of Linux like Ubuntu, Red Hat, CentOS, etc., and so on. You can have Windows as well. Drawback of virtual machine is that it's slow. It's slow to create. It's slow to start up. It's slow to recreate and so on. So you'll basically end up installing the operating system. You'll install your applications. Then after that, you'll have to boot up your virtual machine, which can potentially take quite a few minutes, depending on how many services or how many applications you have installed in the virtual machine and so on. So it's often slow to boot up, to create, and to recreate and so on. And often virtual machines are also called pet. So a pet is something that you care for. You name the pet, you nourish it. You, in case of virtual machine, you basically spend time in installing things. You name it, then you install the service packs, etc., and so on. And in most cases, you cannot afford to lose the virtual machine the image, basically, because if you lose the virtual machine image, you'll have to recreate it, which will be very time consuming. Whereas containerization is software level based technique. It's a software level technique which does rely on the BIOS settings as well. So your motherboard needs to have VTX or VTD enabled, or in case of AMD processor, you'll want to have AMD V enabled. It's basically a CPU level switch or a feature which needs to be enabled in the BIOS. Once you have enabled it, after that, everything gets simulated at the software level. It's very, very fast. Sorry. Sorry. Okay, so containerization is very, very fast because in a matter of minutes, you can create a new container. Or actually, let me put it this way, you can create a new image. After you have the image created, you can start up the container in a matter of a second or a couple of seconds, basically. So in just a few seconds, usually it's just a couple of seconds or so, you can start up a container. Your application will be up and running. Your database will be available. Everything will be there. So basically, it's very, very fast to start up a container. I'll show you that practically in just a bit. The only minor downside to containerization is that it's a Linux-based solution, which means that you need to have some flavor of Linux, or even if you have Windows and you still want to use this containerization solution, then for that purpose, you can choose to utilize containers that are supported by a Windows Server. The Windows Server, especially 2016 version, has its own way of maintaining the containers. Otherwise, if you are trying to use Docker, which is a containerization solution, and you want to use it on top of Windows, then in case of that, you basically have to install Docker Toolbox on Windows, which will end up installing VirtualBox, and inside the VirtualBox, it will create a Linux-based image, and then inside the Linux-based OS, it will end up creating the containers. So it's still possible to run Docker on Windows, but you have to utilize VirtualBox for that purpose. Alternative to Docker is LXC, or Linux container in short, but it doesn't run on Windows at all. You cannot even virtualize it unless and until you use a virtual machine. You have to run Linux inside virtual machine, then you have to create the Linux container inside it and so on. But we prefer using Docker because Docker is supported by Kubernetes. It's a very popular solution for creating containers, basically. So containers are very fast to create. Why they are fast to create? Because it actually shares the host operating system's kernel. It shares the host operating system file system as well. So due to the sharing, it at the software level, at the file system level, it makes things much faster to create as well as to start up and so on. And when you create a container, it's very fast, which means you can create multiple containers. And containers, by default, they are isolated. They are independent of each other. You can still expose some ports so that some ports will be available to other containers. They will be able to communicate with each other and so on. But by default, they are isolated, basically. So basically, you'll want to create a container and contain this product component, which means the database and the product service should be running inside a container. Or if you want, you can choose to create two containers. One container just for running the database server, and one container just for running the REST-based services. So you can choose to create two containers for this purpose if you want. And often containers, they are called cattle, because cattle, you usually don't name the cattle. You name the pets, but you don't name the cattle. And if you lose the cattle, it's usually fine. You can replace that cattle with some other cattle. In case of containers, when you lose a container, in a matter of few minutes, you can quickly create another container. You'll be up and running with a different container and so on. We usually use Kubernetes on top of containers. I'll talk about Kubernetes later on, but for now, keep in mind that Kubernetes is basically a container orchestration solution. It orchestrates multiple containers. I'll talk about that in the next chapter. For now, just keep in mind that container is sort of a virtual machine. It's isolated. It's not running at the host OS level. It's running inside an isolated environment. How do we use Docker? So detailed discussion is a bit out of the scope of this particular webinar, but still I'll try to show you some demo so that it makes sense. We do have full-blown advanced or a detailed course available on this particular topic where we cover everything end-to-end. We usually have the labs as well and so on. Okay, so here on my side, I'll give you a quick demo of Docker so that it makes sense how we can utilize it so that by the time we are discussing Kubernetes, you'll be familiar with Docker concept. Okay, so Docker basically heavily relies on images. Just like we usually have ISO files for the CD or DVD images and so on, likewise, we can have images of the Docker container. So think of image as some predefined configuration. Like you can have some predefined operating system. You can install some operating system yourself and then save it as an image, or you can choose to download some off-the-shelf image as well. So Docker, I already have Docker installed on my machine. Before I start using it, let me show you that you can connect to a website which is called hub.docker.com, where you can search for some ready-made images. Say you want to utilize Ubuntu as the base OS for your container. You can search for, let's say, Ubuntu. You can see what versions are available, and then you can download this image, and then you can later on fine-tune it further and so on. You don't have to ever download any image at all. You can choose to create a new image from scratch as well. But usually it saves a lot of time if you do download some ready-made image. So here we have quite a few versions available. Like we have the latest one as well. If you scroll down, you'll see some older images as well. So we can go to, let's say, command prompt here. You can search. You can use Docker search here as well. It will also connect to that hub.docker.com website. Show you various images that are available that you can download any image you want. For downloading the image, you can use Docker pull. You can specify what image you want to download. So let's say we want to download Ubuntu. Let's say I want to download 14.04 version. I'll not literally install this one because I do have quite a few images pre-installed here. I can show you the list of images. I do have couple of custom ones like my dev Ubuntu, they are there. Then I'm also using Kubernetes. For that, I'm using OpenShift. OpenShift has also created quite a few images here. For now, ignore OpenShift ones. I'll talk about that later on. So here we have a couple of custom images basically. In the full-blown course, we covered how we can create our own custom image from scratch. Whereas here, I'll just show you how we can connect to some image that we have already customized, how we can issue it some commands, etc. and so on. Okay, so for the connectivity, if you want to connect to some image and you want to perform the operations, you can use various commands. So for example, I'm going to use this Docker run command. I can choose to give it some name, or for now I'm going to be a bit lazy. Just tell it I want to create an instance of this dev Ubuntu. Or let me actually show you how to create a simple image from scratch as well. So for this purpose, let me show you the script here. Okay, although you can issue the commands manually to create a new image from scratch, but usually the best practice for the sake of automating things is to create a file, name it Docker file, and then inside the Docker file, you have to use its own script or the scripting syntax. You can always Google for it. Plus, I've also mentioned some of the commands in the PDF file as well that you guys have. So basically, we can we can specify some base image. So here, rather than using the full-blown Ubuntu 14.04 sort of image, I'm relying on some image which is created by some other person. This person has opted to share this Ubuntu 12.04 image with the rest of the world. It already has JDK 8 installed inside the image. So one option is to download a plain vanilla Ubuntu image, then customize it by installing JDK, Maven, Git sort of tools and so on. Or second option is to just find some image which already has pretty much everything pre-installed that you need to use. So here, I'm going to use this particular Ubuntu 12.04, it already has JDK8 installed in it. So from will basically let us use some existing image as a base image. If it's already there on the hard drive, well and good. If it's not there, it will connect to the hub.docker.com website, download this image, and then it will let you customize it. And then after that, I'm using this copy command. Copy command lets us sort of deploy or upload or add files to the image. So here I'm assuming that I have a simple jar file on my hard drive, and I want to add it to the custom image. So think of it as creating a custom image which will have JDK8 installed, plus it will have your custom application deployed as well. Think of this application as a web service. In reality, it's not a service, but for now, just assume that it's a web service basically. So basically, we have the simple script. We can run this particular command to create a custom image out of it. We can name it whatever we want. So let's say I'm just going to call it my dev. I can assign some tag to it as well. Then I'm going to say I want to read the Docker file that I have on the hard drive. So this is a very small image. I already have it on my local hard drive. So it took just a second or so to create a custom image out of it. So it basically used this as a base image, and it deployed this particular application inside it. In more real-world sort of scenario, where you have web services, we usually get to use another command, which is expose. Then we specify what port we want to expose, so that outside the container, the port should be accessible. We should be able to connect to the service and so on. So for now, I just have a simple jar file basically. So once we have this particular image, we should have the ability to connect to this particular image. So for that, I can use, let's say, Docker run. I can specify this my-dev:1.0. Then I can also specify the command that I want to execute. I'm going to connect to the terminal that we have inside the container basically. So in just a couple of seconds or so, we have started a container. If you had a virtual machine, you had some image, like in VMware or VirtualBox, you had some image, and you had to boot it up, it would have taken at least a minute or so to boot it up. Whereas here, we had the image, and we wanted to start it up. The container is up and running in a matter of a couple of seconds. That is it. So now we are inside the container. So whatever commands we execute here, they will get executed inside the container. So here, let me go to the root folder of inside the container. Then I can choose to execute this jar file. So it's a very simple program which will simply display a message on the screen. So here we have hard-coded. Let me simple.greeting. So here we have hard-coded the simple message good. So it's basically executing the application that we have deployed inside the container. Although in real-world scenario, you'll want to have a service-based scenario, you'll have a REST API, you'll want to test it out, you'll have some web server like Nginx, Apache web server, or you'll have some application server like Tomcat, etc., and so on. But here in this scenario, I don't have the service right now. I'll show you service-based example later on. But now I have a simple Java-based application which is deployed inside the application, inside the container basically. Now I can exit out from the container. I can go back to the host machine. I can also then quickly remove or stop the container. Let me first of all get the list of containers that are already running. So here we are connected to this my dev. So I can choose to stop this container. So Docker stop. And notice that this container has a name assigned to it automatically, or you can choose to use this ID as well for the sake of stopping it. For now, I'm going to use this auto-generated name to stop the container. Then I'm also going to destroy the container. Before I destroy it, notice that I've shut down the virtual machine. This is what this command is equivalent to in case of virtualization. I've stopped the container basically. I can start it again, and it will again get started in a matter of seconds and so on. So for starting it again, if I execute this command again, in just a second or so, we have the container up and running. I can exit out again. I can stop it again. Docker stop. DaVinci. Okay, then I can also destroy this container. I can use rm command. The container is destroyed. I can recreate this container. in a matter of a second or so. So basically, containers are very, very fast to create, to destroy, to recreate, and so on. So basically, here we have seen some of the core concepts. So just keep in mind that containers, they are super fast to create, to recreate, to destroy, and so on. That's why they are also known as kettle, basically, because we usually don't care if we have lost a container. We can quickly recreate it in a matter of few moments and so on. So they are very fast to utilize. That is why quite often we get to use container concept, especially in testing environment, or we also get to use it in production environment as well. When we use Kubernetes on top of it, we will have the ability to have automatic failover, load balancing, etc., and so on. So it will make things much faster, basically, or much more stable as well, and so on. So Docker overall is a containerization technology which allows us to contain the related pieces of certain component or certain software and so on. Think of it as a virtual machine, basically. But compared to a virtual machine, it's super fast to create, recreate, and so on.
So compared to virtual machine, in virtual machine, I can allocate certain size of RAM, certain number of CPU cores. I can allocate it. Here, if assuming that your simple greetings program is using certain amount of memory and certain parallel threads, if it wants to open it, how we can restrict that thing and how it controls it, or can you give some idea about that? How does that work?
Okay, so good question. So basically, question is that just like in virtualization, usually we have the ability to control how much resources we want to allocate to each and every virtual machine. So what if you want to do the same in case of Docker containers? So that is still possible. For that, you have two options. You can choose to use some orchestration sort of solution, like Kubernetes does have the ability to control how much resources you want to allocate, but not at the container level, but at the pod level. I'll talk about pod in detail later on, but still overall, it does give us control over how much resources we want to allocate to a certain unit. For now, I'm just going to use the term unit rather than using the term container, because in Kubernetes, rather than focusing on individual container, we focus on the collection of containers. So we can use Kubernetes for that purpose, or what we can do is we can create the container, install the application server inside the container, then at the application server level, web server level, we can control the resources. Like in most cases, most of the application servers and web servers, they come with configuration file where we can restrict how much RAM we want to allocate to a certain application server and so on. So basically, we have to control it at the application level rather than controlling it at the entire container level.
So Docker out of the box does not have any facility like that.
That's correct.
If my application, that like the simple greetings, if it is using 10 parallel threads, when this application started automatically start consuming the resources available on that virtual machine or physical machine, and it tries to create the number of thread that application requires. Correct?
So exactly, it's out of the box. It doesn't have the functionality like we have in virtualization.
Okay.
Okay, so basically here we have discussed that containers are very, very fast to create. The easiest way to understand container is it's like a virtual machine, but it's on steroids. It's very, very fast, basically. So that is why in continuous integration sort of scenario where you need to automate things, you need to say as developer, when we click some button, it should automatically compile the code, check out the code from repository, compile it, and then deploy everything as well automatically. So when you want to automate the deployment as well, containers are definitely very, very useful for that purpose. So I'll come to automation as well later on. For that, I'll discuss Jenkins. For now, we have just discussed Docker concept. It allows us to contain multiple related portions of a component together. Like we can have a database. We can choose to have both the database server as well as the application server, along with the REST services and so on, deployed in a single container if you want. Or you can still choose to split it into multiple containers. You can have one for the database only, one for the application server or the REST service portion only. So you can still choose to split it even further if you want. It actually depends on, do you want to later on get rid of both things together? Or do you want to say that, no, we should be able to get rid of just the REST service portion, but we need to keep the database portion up and running, because maybe there's a chance that some other component which will be running in a different container wants to connect to this particular database. So if you think that one of these two component or subcomponents will be used by some other component, some other portion of the application, then it's better to create multiple containers. So this way later on you can choose to destroy one container without affecting the other container, other portion of the application and so on.
Assuming that we are creating multiple containers, one container is for application servers, assuming that NGINX, and the second is for, let's say, MongoDB database. So in MongoDB database, it needs to write data into some physical files or anything like that. So how are we going to specify the where the location where the data will be written as for the database files? And if we are running multiple containers for MongoDB, they all will point to the same folder location to write the data and to read the data?
Okay, so good question. Exactly. So basically, by default, the file system of the container will be utilized. So each container will have its own mini file system. But if you want to say that, no, you don't want to use the mini file system because you want to destroy the container later on, but you want to keep the data intact, then in that case, at the host level, you can specify sort of a shared folder basically that will be accessible by the container, and it will write the data to the host file system. So this way, when you destroy the container, you will not lose the database.
So if we use the host file system, this is the best practices generally used when we create any database containers?
Yes, exactly, especially in production environment. Otherwise, in case of test environment, you can choose to just destroy the data.
So if we use the host file system for containerization and for the database, so if we the more number of containers we create, it is going to create the same bottleneck because it's going to use the same file system. Isn't that if I create 5 containers pointing to the same file system and make a cluster or something, then it will they all will start writing into same folder or same file location. Doesn't that creates a bottleneck or huge I/O on the same thing, and the performance eventually will get downgraded?
Exactly. So performance-wise, better practice would be to have multiple physical machines as well, and then run a few containers per machine rather than running all the containers on the same machine.
So if we are running multiple host machines, then how the data will stay consistent?
So for that, we can utilize the SAN or NAS, etc., or RAID, etc. So basically, we will still have the common hard drive available to multiple machines as well.
Okay.
Okay, so basically here we have discussed some of the Docker container concepts. In the full-blown course, we cover all the details, like what commands we usually use for creating a new container from scratch, or creating a new image from scratch. How do we import, export containers or the images, etc., and so on. Okay, then next we can discuss Kubernetes. So we can go back to the chapter that we skipped previously, which is chapter number 3. And what I'll do is I'll combine chapter number 3 and 4 because they are both Kubernetes based. So here I'll focus on the important concepts, and I'll discuss how to utilize Kubernetes. Okay, so Kubernetes. First of all, we should be aware of the concept. What exactly is Kubernetes? Why use it? So basically, in the previous chapter, we discussed containerization, or to be more precise, Docker containers. Kubernetes takes Docker container concept to next level. So rather than creating one component at a time, and each component will contain just a specific, or each container will contain specific components, software like a database server, application server, and so on. What if you want to have load balancing in place? What if you want to have automatic failover in place? Then for that purpose, we get to use Kubernetes basically. So Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. It's a containerization orchestration solution. It orchestrates what should happen in what container, and if the container goes down, what should happen, how should we reduce the load on each and every container by having load balancing in place, and so on. And it also basically automates things as well. So Kubernetes, you just tell it, this is my Docker image. Take that image and then create the container space from that. Have load balancing in place. Have automatic failover in place. So automatic failover, load balancing, these are the two major benefits of Kubernetes. It definitely is recommended that we should utilize Docker container for the sake of utilizing Kubernetes, although it's possible to utilize other technologies as well, but out of the box, it's optimized for Docker containers. Then Kubernetes, how do we use it? Although we have other options as well, like we have Docker Swarm, etc., and so on, but we are going to focus on Kubernetes here, which is the most popular solution. Okay, so if you recall, we discussed in microservices that in a microservices architecture, ideally we should have we should design the services for failure. So this is exactly what we are going to discuss now. How do we ensure that if the service has failed, then it shouldn't really fail. It should just fail over to some other instance, etc., and so on. So we should have automatic failover. We should automate things as well, and so on. So before we see it practically, we should be aware of some of the terms that we get to use in Kubernetes. Okay, so we have various terms like master, node, pod, and so on. We also usually have replication, etc. as well. Okay, so let's cover some of these terms. Okay, so what you will have is, you will have your, let's say, database. You will have, let's say, your REST API as well, or REST service for the product component, let's say. Let's say that this is running inside one container, so container 1. This is running in a different container, container 2. So we have multiple containers here. When we use Kubernetes, which allows us to orchestrate, it allows us to have load balancing in place, automatic failover in place, and so on. It says that we can have multiple containers, and then it groups these multiple containers together and calls these a pod. A pod is composed of at least one container. Otherwise, we can have multiple logically related containers inside a pod. Kubernetes has built-in support for implementing automatic failover. For automatic failover, we basically get to replicate the pods. So you can tell Kubernetes that this product portion or component of our application is very important. It should always be up and running. And they should also be load balancing as well, because we will have way too many customers trying to access this particular component at the same time. So for load balancing purpose and for automatic failover purpose, you can instruct Kubernetes to replicate this pod. You can scale this pod basically. The scale means how many pods you want to have. So you can say, I want to have, let's say, 3 simultaneous pods. So it will basically automatically replicate the same structure 3 times. It will have the same containers as well. And it will automatically perform load balancing as well. It will automatically redirect the traffic. And if one of the pod goes down, it will automatically switch over to a different pod. And if you tell Kubernetes to always ensure that we have 3 pods available at a given time, it will, if one has crashed, it will automatically start another container, or it will create another pod. In the pod, it will automatically start these containers automatically. So basically, at the pod level, you can implement scaling, you can implement the failover and so on, and load balancing as well.
So when we define pod, we need to specify the IP address and the port number for that thing, so that every other external microservices can access to that single IP address and port, and behind that wall, these cattles can be scaled up and down depending on the numbers defined.
Exactly. So yes, IP address wise, you can specify the IP address, or you can specify the host name as well, which is actually also known as the root. So you can implement routing basically. You can define the routes. I'll talk about routes as well. So root is sort of equivalent to IP address and port number and so on. Okay, so we can have the pod here, and then you can have multiple pods. So this is just for the product which we have scaled. So likewise, you can have another pod which can, let's say, be for a different component of your application, like let's say customer. So it will have container number 1 for the customer REST service, container number 2 for the database, and so on. And again, you can choose to scale this one as well. And if you have multiple pods, you can definitely run as many pods as you want on your machine. But if you want to sort of implement failover at the system or at the hardware level as well, then you will not want to have everything running on the same physical machine. So in that case, you can say these pods, they are running on machine number 1. So that is also known as a node. In Kubernetes, we call this a node. Node is either a physical machine or it's a virtual machine. So Kubernetes can utilize virtual machine concept as well. So inside a virtual machine, you can have these pods running, and each pod can have multiple containers that are logically related to each other. In most cases, you'll want to use virtual machines these days, especially if you don't have too many physical machines available. Otherwise, if you don't have any issues with physical machines, you have lots of them available. Go ahead, you can install or set up Kubernetes nodes at the physical machine level as well. So you can have multiple nodes basically. One small node or a node, just in case if we have utilized Kubernetes in the past. In the older version of Kubernetes, each node used to be called a minion. So minion used to be the older name for node, whereas these days we call it a node. So we can have multiple nodes. A node can have multiple pods. Each pod can have multiple containers. Then one more important concept is Kubernetes has something that is known as the master. So master is basically responsible for managing all the nodes, ensuring that if one pod has gone down, then it should automatically fail over to the second pod, and so on. So master basically orchestrates everything.
Is there any secondary master concept is also available in case the main master dies?
No. So we just have one master.
So in case of that, something happened to that machine, the entire thing is vulnerable, right?
Exactly. So in that case, at the system level, we will have to implement the failover. Just like in case of, let's say, Windows, etc., we have the failover cluster available at the operating system level. Likewise, we can implement the same concept at the entire OS level, at the entire machine level, and so on. Okay, so basically this is the overall architecture. Then one more small note. Each pod is composed of at least one service as well. So think of service as your final output, or to keep it simple, if you recall, I discussed that this is a customer service REST API basically. So think of this as the service basically. So even at the Kubernetes level, we use the term service. It basically lets you see what services are exposed by any container running inside the pod. So it will show you the URL for that particular service. You can access that service by using that particular URL and so on. Okay, so this is the overall architecture. Then Kubernetes installation can definitely be fairly complex, especially if you do not use any other platform or any additional software, etc., and so on. So Kubernetes, if you try to install it from scratch without any additional software or additional tools and so on, it will be fairly complex. To make it a bit simpler, you can utilize something that is known as, let me show you the list of the software actually. So the best option is OpenShift, but before that, let me discuss another option here. or it might be mentioned in the previous chapter. Let me double check. So yes, it's available here. So you can choose to use Minikube if you want. Minikube is okay for simpler scenarios where you want to have exactly one node. So if you recall, I mentioned the node concept, where you can have this node, which is composed of multiple parts. So if you are okay with having a single physical machine or a single virtual machine which contains multiple parts, you want to have a simple setup basically, then Minikube can be used for that purpose. It does make things much simpler. I've mentioned the details here, like how you can download, how you can set it up, and so on. It does make things much simpler. But at the same time, it's not very useful in production environment, especially where you want to have multiple nodes. So again, if you're okay having a single node, it's fine to use Minikube. But if you want to utilize multiple nodes, Minikube is not good for that. So for that purpose, you'll want to use another thing which is known as OpenShift. So I've mentioned OpenShift as well. Where it is, I've mentioned it in the next chapter actually. So Minikube, you can use it for learning purpose if you want. Otherwise, if you want something that's more production ready, then for that purpose you'll want to use OpenShift. So OpenShift is actually covered in the last chapter along with Jenkins. So we are still basically discussing Kubernetes. Before discussing the last chapter, we focused on Kubernetes. They were covered in chapter number 3 and 4. Okay, so OpenShift. OpenShift is perhaps the most production-oriented way of utilizing Docker and Kubernetes concept. It's a platform basically which allows you to utilize Kubernetes and Docker concept with much more ease. It makes the installation, setup, etc. much easier rather than using just the plain vanilla Kubernetes software setup, which is very, very complex. You can use this OpenShift. So think of it as a platform which makes the setup, management, etc. much easier. It's created by Red Hat. It's open source. It's also a containerization or container orchestration software basically. It basically doesn't do anything by itself. It just lets you install and set up and manage Kubernetes with ease basically. So under the hood, it's still making use of Kubernetes. Okay, so again, OpenShift installation, setup, etc. is out of the scope. We covered that as part of the full-blown course that we have. But for reference, I've mentioned some of the commands here. So on my side, I already have OpenShift installed. Now, before I show you OpenShift, or let me actually show you OpenShift first of all. So OpenShift basically supports command line interface. It has the CLI as well as the web-based portion as well. It allows you to take any Docker image which you are responsible for creating. So inside the Docker container or the image, you'll want to ensure that you have all the software that's required by the service. Like you'll want to have the database, you'll want to have the REST API, etc. and so on. You'll want to expose that REST API over some port and so on, and then you'll want to save everything in a Docker image. So to some extent, in the previous chapter, I showed you how we can create a Docker file, how we can specify what base image we want to use, what additional software we want to install, what files we want to copy it into the image, and so on. So once we have the Docker image, we can feed it to OpenShift, which will automatically talk to Kubernetes and deploy the image inside the Kubernetes basically. And by the time it's done, you will have your service up and running. Whatever services are there in the Docker container, they'll be up and running. And then after that, you just have to manage the services. You can manage what port number you want to utilize, what IP address you want to utilize. You can specify how many replicas you want to have, and so on. Now, setting up Kubernetes and executing the commands for uploading the Docker container or the Docker images and so on, they can be a bit time consuming. So obviously, we don't have too much time in this particular webinar. So what I've done is I've recorded the video here. Usually we cover all these things in much more detail in the full-blown course that we have. where usually the attendees get to perform hands-on activities for installing and deploying everything and so on. Here, we don't have too much time, so I'll just show you a quick overview of how we get to utilize Kubernetes. Where did I save the file? Okay, so here in this demo, we will see how we can start OpenShift. OpenShift is basically a sort of a server or sort of a service. You have to start it up. After that, you have to feed it the Docker images, which contains your services, etc., and so on. So I'll quickly show you some of the commands that we use for the sake of starting OpenShift. So for starting OpenShift, we get to use OC clustered up command. This command will start OpenShift, which under the hood initializes Kubernetes and so on. Then once we have initialized it, we can choose to log in. So here we are using OC login to connect to OpenShift. So we can execute commands as the administrator. Then we can create a project in OpenShift. Think of project as what pods you want to create as part of that particular project. What services you want to deploy as part of that project. Or in other words, we can say, in most cases, you'll want to have one Docker image per project, basically. So here in just a bit, I'll show you the command that we can use for uploading a Docker image, which contains our services and so on. Okay, so here we are using this particular command. Where did it go? Okay, so OC new app. We're creating a new application. It's an OpenShift-based application, which will read this particular image file. It's a Docker-based image. It's a simple hello-based service. We have used a simple service, REST-based service here, which will simply display hello world message on the screen, basically. So we have a simple service here in this particular image, and we are telling OpenShift to take this image and then deploy it. The deployment is very, very easy. You just feed it the Docker image, basically. Then after that, you can see what exactly got deployed by looking at services. You can see what pods got created by that particular Docker image. So here we can see OC get pods is showing us that we have this particular pod. So hello OpenShift is basically whatever the name of the image was. Then after that, it just adds some distinct numbers and alphabets. And when you scale your pods, when you say you want to have multiple replicas, it will basically just add different digits and alphabets to it. Whatever we have in the beginning will remain as it is. So currently we have just one replica, basically. After that, you can connect to your OpenShift management console to see what services are there and so on. You can type in the IP address, and by default, it uses port number 8443. Type in username and password. Then here you can see your project. And once you're connected to your project, you will be able to see your pod. So here we have one pod. Hello OpenShift is our basically the overall application, which is composed of this one pod. And we have one replica of this particular pod. Then you can also look at what services are there inside the container of that particular pod. So for that, you can go to your applications, services. Here it's telling us that we have hello OpenShift service. Currently, it is not exposed over any port number, or in short, we are not able to access it from the host machine or from any other container at all. So for exposing the service so that other applications, other containers, the host machine should be able to access it as well, you can choose to create the root by clicking this particular hyperlink right away here. Or for the sake of automation, since we do want to automate things, because later on we will discuss Jenkins, which will be used for the sake of automating this whole process. So for the sake of automation, you'll want to avoid using the GUI as much as possible. Instead, you'll want to use the command line based options. So for exposing, we get to use OC expose command. So OC expose, then we specify the name of our service. We specify what sort of domain name we want to use or host name we want to use. So here we are using simple host name for now. We just have localhost. Otherwise, if you have DNS server, you can definitely specify some fancy name as well, like myservice.whatever.com, etc. and so on. So we are exposing the service. As soon as you use that OC expose command, it will show you the host name here right away. which means that now the service is exposed. And when you click this particular link, or when you try to make use of this link in, let's say, JavaScript or HTML, etc., and so on, it will let you access this particular service. It's basically a REST API. It's a simple API. It has just a single get action right now. It will simply show us this message for now, hello OpenShift. But obviously, in real world scenario, it can return you list of records like customers, products, etc., and so on.
So from what I can see is the subnet, local subnet was 172, and then this OpenShift is and the regular enterprise network, it's a different IP address. If you go like 10 seconds back in the video.
Yes.
So it says that 172.30, that's the subnet IP address of the container pod, or the pods, right? Of the all the pods. And now then we are exposing it so that all the traffic from 192.168.129 can be redirected to this thing. And the same thing that Docker does not provide out of the box, the routing local thing, whatever. If I run it from to access it from the outside IP address, we have to use the same process like expose and everything, but there is no other there is no out of the box routing options available
in a Docker.
Yes, in the Docker, because this one is we are using Kubernetes, and then then we are doing all the Redshift and all that thing. But if simply Docker, is there any commands that we can use to expose?
There is. So if you want to use just Docker and you want to expose a service, then for that, let me show you the full command here. It's this one. So Docker run port number. This is the internal IP or the port. This is the external, and whatever service we have inside the Docker container.
Okay, and if we have to, and in Docker, if we have to run the same container on multiple machines, then we might have to probably use the swarm mode or something. Then only we can use this thing, right? Otherwise, we have to go with the Kubernetes and then that Redshift.
Pretty much. So you can use a swarm, or if you don't want to use swarm, you want to use Docker only. Then in that case, you can choose to export the Docker container as an image. Then you can import it on a different machine. So you'll have identical container on both the machines. So export and import functionality is available in Docker.
Okay, sounds good. Sorry to interrupt.
No worries. Okay, so definitely feel free whenever you have questions. Okay, so basically here we have discussed how we can use Kubernetes. And another major benefit is that you can use scale options. So you can basically use either the graphical technique, or you can also use the command line technique. Just click the up arrow, it will increase the number of pods. So we are scaling up the pods to 2 now. So now we have 2 identical pods with identical containers, and if one goes down, second will automatically take over, and load balancing will happen as well automatically, and so on. So now we have 2 pods basically. They contain identical containers, and you can see that the initial portion of the name is identical. It's just the last few characters and digits that are slightly different. You can also see how many pods we have from the command prompt as well. So basically here we have seen how we can deploy any Docker image in a clustered sort of environment by utilizing OpenShift platform, which automatically uses Kubernetes and Docker containers concept. Then next, you'll also want to automate things as well. So for the sake of automation, rather than running the command line based tools manually or using the graphical tools manually, you'll want to say that as a developer, say we are using some IDE like Eclipse or IntelliJ or NetBeans or Visual Studio or Visual Studio Code or whatever. And as soon as we check in the code into the repository, like Git, SVN, CVS, and so on, we should automatically compile the code. We should automatically generate the output binary files like DLL, EXE, jar, web application archive files, EJBs, etc., and so on. We should run the unit tests automatically. And then after that, we should deploy everything inside, or we should create a Docker image. And then we should deploy that Docker image in the clustered environment or in that OpenShift environment, basically, which is making use of Kubernetes and so on. So basically, you want to automate everything. say there are lots of developers. Each developer is going to check in the code into the same repository, which will happen in real world as well. And as soon as you check in the code, it should produce the final output automatically. It should deploy everything inside Kubernetes automatically, so that the service should be up and running. So we want to automate everything. So this level of our automation is also known as continuous integration / continuous deployment. So your okay.
If you don't mind, I will asking. So what I understand is when the developers push their code into repository, we build it and then we deploy it to the real production environments. So that's the goal. But assuming that one of my container, which I am changing it, which endpoint and the input communication JSON and everything is changed. So in that case, all the connected components will start failing, right? If I just deploy that container and it has a break in changes. So what is the general best practice in the market when they deploy any new containers, but that supports different format? Let's just a simple order update services there, microservices, and that has a different set of we just change few fields in it in the REST file. And if we start deploying it, it will fail, right, with the connected components.
Exactly. So in that case, what we usually do is, so basically our goal is to utilize Jenkins for the sake of automation. And to answer your question, what you'll want to do is you'll want to ensure that you build the jobs in Jenkins in such a way that they are sort of chained. So say that we have independent component. This is, let's say, independent component number 1. Then we have dependent component number 1. We have dependent component number 2. It depends on, let's say, 1. So we have dependent component. It depends on 1, and let's say it's 1.1. So this should be sort of deployed after we have deployed independent component, and then this should be deployed after we have deployed this dependent component number 1. So this is sort of the sequence in which we should deploy the code and so on. So if this is a Jenkins job, Jenkins job is basically sort of a project. So we can say that we should have this job. It should be responsible for creating the image, Docker image, and it should deploy this Docker image inside Kubernetes environment or in OpenShift, basically. It should delete the older one and it should deploy the new one. It's independent. And once this has done, the second, we should have another job as well. The job number 2. So, as part of job creation, we can tell a job that it should be triggered when some other job has completed its work. So we can say when this job has completed the work, which is totally independent, it has deployed the Docker image, it's now available inside Kubernetes or in OpenShift. After that, we can start job number 2. It will create another Docker image and it will deploy it inside OpenShift as well. And then after that, we can say when job number 3 starts, it should start only when job number 2 has completed. It should do the same thing. It should create its own Docker image. So let's say this is for product. This is for, let's say, customer. This is for, let's say, sales. So for now, we don't care whether product, customer, and sales, are they really dependent on each other or not. For now, we are assuming that, yes, they are dependent on each other in this particular order. And each component, job will end up creating its own Docker image, and it will deploy it inside OpenShift, basically.
So if OpenShift start deleting the running containers and the containers are accepting the request, so we will have loss of service or we'll have some downtime. So generally, this is the way they do it, or because if we try to deploy anything which is running, we'll have loss of service. We'll lose some of the requests.
Yes, so definitely. Ideally, we should do it in a testing environment, and if you have any staging environment. After that, if downtime is not avoidable, then definitely there's no choice. We have to interrupt the service temporarily. Then we can promote it to production environment. And then we can bring all the services up and running and so on.
So
downtime is
all the public facing websites like big names. How are they avoiding the downtime and while deploying the new changes?
So they are basically ensuring that whatever microservices that they have, they deploy the independent components first. So they run the job for the independent component first, just upload that particular portion, then the rest of them, and so on and so forth.
For dependent components for public facing website, how are they rolling it, like for banks and all that thing, right? So how are they doing it, banks or social media and other big companies?
Exactly. So in that case, so basically you'll mostly have session involvement as well. See, your data is stored in the session. So rather than storing the session-based data in the process, in the web server process or the application server process, they basically externalize it. They store it in the database. So most technologies like Java, .NET, etc., when we use session, like in case of, let's say, .NET, in the web.config file, we can utilize session state, and we can specify that we want to save the session state in an external SQL Server-based database. So this way, when your service is deployed, it is just overwriting the services, not the database itself. So database still contains the actual session sort of data. And when the new service has been deployed, it will basically still be able to read the same session data of the database.
Thank you. Thank you so much.
You're welcome. So both .NET, Java, and actually even other major technologies all support this externalization of the session-based data on some database and so on. Okay, so for the sake of automation, basically we have to utilize some software which should automatically check out the code, compile the code, then generate the Docker images, deploy them in OpenShift, etc. Start the application, ensure that the routes are created properly, everything is up and running, and so on. So for that purpose, quite often we get to use Jenkins. So Jenkins, in the full-blown course, we covered it in more detail. For now, I'll just quickly give you a quick overview of it. Where did I say this one? Okay, so Jenkins-wise, you'll want to, first of all, create some application. So here I'm going to create a simple Node.js based application where I'll have a simple service basically. So here we have a very simple REST API. It's going to listen on port number 9090, and when it receives the get action at the root level, it will simply return hello node.js version 1.0. It's a very simple Node.js based service. You don't need to use Node.js. You can choose to use the Spring Boot, you can choose to use a web API or ASP.NET MVC and so on. So we have a simple service. For now, we are testing it in standalone way. So when we try to access port number 9090, it's showing us a result like this basically. Then in a real world scenario, obviously you'll want to automate everything. You'll want to ensure that we have Docker images, etc. and so on. So for that purpose, here we are going to first of all create the Docker file so that we can create the image. So here I'm going to use the image. It's named Node. Its version is Boron. That's the official version name used by the Node-based Docker image. It already has Node.js pre-installed inside it basically. There I'm creating a working directory, and then I'm copying the Node.js specific configuration file, which is a package.json file. I'm installing the application inside it, and I'm exposing the service on port number 9090. And then I'm executing the service inside the container by using node index.js, the very last statement basically. It's going to start the service by using the last statement. So we have this Docker file, and for the sake of automation, we're going to utilize Jenkins. Even before using Jenkins, here if we execute this Docker build command, it will basically build the image. So here it's building the image. Obviously, you'll not want to build the image manually at all. You'll want to rely on automation. For that, we get to use Jenkins. So for Jenkins, let's go to the Jenkins portion. So for Jenkins, let me. So this is all manual stuff. I want to show you the automation portion. So let me go to the automation right away. Okay, so for automation, we are inside Jenkins now. We are accessing Jenkins page. Then we can skip configuration portion for now. Okay, so we are creating a job. You can choose to create a regular freestyle job, or you can choose to create a pipeline. So if you create a regular job, you can specify what repository contains your node.js application along with your Docker file, which will create the image and so on. Then here we are going to poll the SCM. So we will we'll connect to the Git repository every minute or so, if changes are detected, it should rebuild the image and redeploy the application. If no changes are detected in the code repository, if developer hasn't checked in any change at all, then we shouldn't redeploy the application at all. Then very importantly, here we have to execute the scripts. So here we are, first of all, building the image by using Docker build. Then we are using OpenShift for the sake of deleting the older service. We are deleting the older image or the distribution basically. And then we are creating a new image. We are recreating the image based on the updated Docker image basically. And basically, that's pretty much it. After that, if you just make any change, so we are assuming that developer has updated the source code. So from version 1, now we have changed it to version 2. Then we check in the change. After that, if you go to Jenkins, without clicking any button whatsoever, it will automatically trigger the build. It will build the new image. It's building the new image here. Then it will deploy the image. It will delete the older application in OpenShift and then redeploy the new image and so on. So basically, you'll always have up-to-date copy of your application. Similarly, you can also choose to create a pipeline as well in Jenkins. So for pipeline, we can choose to utilize pipeline template, then write the script, which will basically execute similar commands that we saw previously. Again, make a change to your source code. As developer, we have changed the code. So now we have just changed it to version 3. Again, when you check in the changes to your repository, Jenkins will automatically connect to the repository and it will see if changes are detected or not. If yes, then pipeline will show us the output as well like this. So it will check out the code, build the Docker image, then delete the older application, delete the older deployment, and redeploy the application inside OpenShift basically. So you'll always have up-to-date version of your application deployed in whatever environment you have.
I understand how it built using the Docker, but how did it push to OpenShift? In the
so for that,
how the Jenkins pushed it to OpenShift?
So for that, we had to use this command, oc new app. It will basically override the previous app. If the app already exists with the exact same name, it will override the app. So the last command basically. So oc new app. If you specify the same image, it will automatically detect whether the application was.
So if there are multiple OC OpenShift are running, or what? How does it know that what is the IP address of OpenShift and where to push this thing? Is there any configuration that we define that if it OC, it points to this IP address?
You can pass it additional arguments as well if you want to specify a remote server. For now, we are assuming that we are running Jenkins as well as OpenShift on the same server.
Okay, well, that's why. Okay, that's how it is. All right.
So basically, this is how we are automating things. So developer is now just responsible for making day-to-day changes to the source code. And then due to automation, due to continuous integration and continuous deployment, everything is getting deployed in whatever environment we have, like test, prod, whatever we have. And we will always have up-to-date copy of the application or the services deployed in that environment.
So along with the presentation slide that you are showing, can we get the copy of these recorded videos as well for our references?
Oh, so unfortunately, the videos, they are part of the full-blown course that we have. So I'll have to double check whether it's possible or not, but I don't think we'll be allowed to do so. We do have the recorded version of this particular session. So we are recording this particular video. So you'll definitely have access to the recorded version of the webinar.
And the presentation that you are showing, that we will get, right?
Yes. Okay. Exactly. So presentation link is there in the chat window. Plus, if you go to the handout section, if you go to webinar software, you'll see sections like chat, and there should also be handouts as well. So in the handout section, you'll see architecting microservices PDF file.
That file is a little different than what you are showing it.
If you are referring. Exactly. Yeah. So if you're referring to this one, let me see if I can. You mean the first one that I showed you?
Yeah, in the first one, quick notes or something, right? Yeah, this one is different. Yeah.
Okay, so I'll just take a quick. I'll convert it to PDF and send it.
No problem. Away.
Thank you. You're welcome. handouts. Okay, so it's getting uploaded. So if you go back to handout section, you should be able to see this file as well. It's 90% done. Okay, so yes, now it's 100% done. It might take a few more seconds.
No
So you should be
problem.
able to see file.pdf. Okay, do you have the file now?
Yes, I received it.
Okay, so basically this is a quick overview of various technologies that we get to use for the sake of automating creation of microservices, deployment of microservices, failover, load balancing, etc., and so on. So any further questions? And you guys do have access to the PDF files, and we will also be uploading the recorded session as well.
Is there anything you can show us about replications?
So replication-wise, basically you have to specify the scaling at the pod level, how many pods you want to have. So right now I don't have the demo for that offhand. Like we usually do have scenario where you can forcefully fail a cluster, or not the cluster, but the pod or the container inside the pod. So that's where we usually notice that it fails over to the second one automatically. But I don't have it available offhand right now.
Is there anything related to Chaos Monkey set on your machine that we can see?
No, currently I don't have it installed. So that's a very good software which can use for simulating failures and so on.
Is that Chaos Monkey has any UI or something that,
Yes.
or it's a command line?
It has both options. Okay, so you guys will have access to the recorded session as well. Plus we have the PDF files. Thank you very much, guys. It was a pleasure to be here with you.
It was really informative. Thank you.
Thank you. Thank you.